In this video, we'll cover how to solve geometric sum problems. Geometric sums are the only other known method that are able to find where a series converges besides telescoping sums. This method can find the sum of where a finite and infinite series converges to. A series is geometric if the ratio between consecutive terms in the sum are constant. But before we get into solving for geometric series, let's look at an example of one. This is the basic structure of a geometric sum series. It's composed of A, the first term in red, and R, the common ratio, which is in blue. Now, how do we find the sum of an infinite series? Well, we could add everything together. We can do A plus A times R plus A times R squared plus A times R cubed, and so on until we reach A times R to the n. But that's impossible, and we're not going to find the sum like that. Instead, we're going to have to use this formula, A divided by 1 minus R, when R is less than 1 and greater than -1. Only under this requirement can we find the sum and where the geometric series converges to. We could also write this as the absolute value of R is less than 1. Now, how do we find R? Well, R is just equal to the second term divided by the first term. Okay, so now that we know the basics around geometric sums, let's look at a real problem. Okay, so here's our first problem. Before we can even solve this problem, we first have to find our R. Our R, if you remember, is equal to the second term divided by the first term. If we look at our problem here, we see that we have 5 plus 1 plus 1 divided by 5 plus 1 divided by 25, so on. Our first term is going to be the 5, and our second term is going to be the 1. We can plug this into our equation. R is equal to the second term, 1, divided by the first term, 5. Now that we've found R, before we plug it into our equation, we first need to see if this series even converges. And we can do that by plugging it in, by checking the requirement. The absolute value of R is less than 1. And we can clearly see that 1/5 is less than 1. Now we can plug this into our equation A divided by 1 minus R. RA is our first term, by the way, which would be 5 divided by 1 minus our R, which is 1/5. This equals 5 divided by 4/5. And we can change this complex fraction by multiplying by the reciprocal of the denominator. And this can get us 25 divided by 4. And just like that, our series converges at 25 divided by 4. Okay, this problem is similar to the last one, so how about you try this on your own? If you don't feel like it, just follow along with me. So for this problem, again, we first want to find the R, which is going to be our common ratio. Our common ratio is going to be the second term divided by the first term. In this case, R3 is our first term, and our second term is our 9 divided by 8. So now if we try to solve for R, we'll do our second term, our 9 divided by 8, divided by our first term, which is 3. This is a complex fraction, so I'm going to multiply by the denominator's reciprocal. It's going to be the 3. So I'm going to get 9 divided by 8 times the reciprocal of 3, which is going to be 1/3. That is going to cancel with the 9, and I'm going to be left with 3/8 as my R. Now we can check this with our 1 requirement. The absolute value of R is less than 1. 3/8 is less than 1. So that means that this is true, and we can plug this into our equation. A divided by 1 minus R. We plug in our values. Our first term, 3, divided by 1 minus the common ratio, which is 3/8. We'll be left with 3 divided by 5/8. We're left with a complex fraction, so we need to multiply by the denominator's reciprocal. That's going to give us 3 times 8/5. And that's going to give us 24 divided by 5 as our answer, meaning this series converges to 24/5. And that is the answer. Okay, so this series looks a little bit different, but I think you guys will still be able to solve it. So if you want, pause here and try it on your own. If not, follow along with me. So again, we have to find what our r equals. So we'll look at the first two terms. The first term being 4, the second term being negative 48 divided by 11. Our r is equal to negative 48 divided by 11 divided by 4. It's an ugly fraction, so we can change that by multiplying by the denominator's reciprocal. So we get negative 48 divided by 11 times 1/4. We can cross out this 4 and the 48, and this will leave us with a negative 12 over 11. Now we get to see if this meets our requirement of the absolute value of r being less than 1. And if we look at this, if we take the absolute value of negative 12 divided by 11, this is actually greater than 1, meaning that this is not true. This statement is not true, resulting in this series being divergent. So it diverges. Okay, so now that we've solved a few problems that are in sum, let's look at what a problem looks like in summation form. To solve this, we need to first find the first term, the second term, and the r. So let's do that. To do this, all we have to do to find the first term is apply this n is equal to 1 to our a sub n. If we plug in n is equal to 1, we'll get our first term is equal to 1 divided by 2, because if you plug in 1 for this power, you get 1 to the power of 1, that's 1, and 2 to the power of 1, that's also 1. Now let's find this 2. If we were to plug in 2, 1 to the power of 2 would be 1, divided by 2 to the power of 2, which would be 4. Now that we've found the first and second term, we can find our r. Our r is equal to 1/4, the second term, divided by 1/2, the first term. We can simplify this, and we can get 1/4 times 2. And this, we can cancel these out, and we can be left with a 1/2. And this is our r. Let's check with the requirements. The absolute value of r is less than 1. 1/2 is less than 1, that's true, meaning we can plug this into our equation, a divided by 1 minus r. Our first term is 1/2 divided by 1 minus 1/2. This will get us 1/2 divided by 1/2. And then we will get 1/2 times 2, which is equal to 1. So this series converges at 1. Okay, here's our next problem. So if you want to solve this problem on your own, try it out. Otherwise, follow along with me. So for this problem, you'll notice that the index, instead of starting at 1, it starts at 2. And that's not going to really change anything. This just means that our first term is going to start at a sub 2, and our second term is going to start at a sub 3. Everything else is the same. We need to also look for our r. So let's look for our a sub 2, which is going to be 3 squared divided by 4 squared. Now, I'm not going to multiply these out to save some time. A sub 3, this is equal to 3 cubed divided by 4 cubed. Now we can plug this into r. we'll use the second term, which is a sub 3, which will be 3/3, or sorry, 3 cubed divided by 4 cubed divided by 3 squared divided by 4 squared. We can multiply by the denominator's reciprocal to get 3 cubed divided by 4 cubed times 4 squared divided by 3 squared. We can use this and cancel out the 3 squared and the 4 squared, and we can get rid of these exponents through simplification, leaving us with 3/4. And that's our R. Our R is less than 1. The absolute value of 3/4 is less than 1, meaning that this series does converge, and we can use our formula. So we can plug in a divided by 1 minus r, and let's make this a sub 2. So our first term, 3 squared divided by 4 squared divided by 1 minus 3/4. This is equal to 3 squared divided by 4 squared divided by 1/4. Can multiply by the denominator's reciprocal to get us 3 squared divided by 4 squared times 4. This will cancel out the 4 and get rid of this exponent, leaving us with 9/4. So this series converges at 9/4. Awesome. Okay, here's our next problem. So again, if you want to try this problem on your own, feel free to pause. Otherwise, just follow along. So this problem, again, it starts at an index of 2. And you'll notice that now we have in the exponent a 2n and in the numerator. And then our denominator is exponent as an n plus 1. It's not going to really change anything when we plug in our values. So let's first find our first term at a sub 2 and our second term at a sub 3 and our r. Okay, so our first term at a sub 2, if we plug in a 2 for our n, we'll have 3 raised to 2 times 2, which is 4. So this is going to be 3 raised to the 4th. If we plug in a 2 for our 5 raised to n plus 1, we'll get 5 raised to 3. For our second term, a sub 3, we will get 3 raised to 2 times 3, which is 6, divided by 5 raised to 3 plus 1, which is 4. Epic. So now we can look for our r. Our r is going to be equal to the second term, which is going to be 3/6 divided by 5 to the 4th, raised to the 4th. Now instead of dividing, I'm just going to skip straight to multiplying by the reciprocal of the first term, just to save time. So we have 5 raised to the 3rd power divided by 3/4. We can begin canceling things out. So the 5/3 will cancel with the 4th exponent. And the 3/4 over here will cancel, and it'll get rid of this 6, but it's going to leave behind a 2. So we'll have left over a 3 squared divided by a 5 as our r. Now this is different because if we were to plug this into our equation to make sure it meets the requirement, we'll see that 9/5 is actually greater than 1, meaning this is not true, or this statement up here is not true, meaning that this series diverges. And that's the answer. Now that we've gone over how to find the sum of infinite geometric series, let's look at how we can find the sum of a finite series. Here's an example of a simple finite sum problem. We could find the sum by adding, and if we were to do that, we would get 1022. But we can also find the sum by using this equation a, first term, times parentheses 1 minus r, which is our common ratio, times n, which is the number of terms in our series, divided by 1 minus the common ratio. And we can only use this formula if our r does not equal 1. And it also works when our index starts at 1. But we'll get into that later. So let's start solving this problem. Let's first find the first and second terms. Next, we can find our r, which is going to be the second term divided by the first term, which is going to give us 2 for our common ratio. Next, we can plug in all of our values into our formula because our r does not equal 1. So our first term is 2 times 1 minus the common ratio, which is also 2. And in our finite series here, we have 9 terms. So I'm going to plug in a 9 for our n. And I'm going to divide this by 1 minus 2. Next, we can simplify this by distributing these 2 across the parentheses in the numerator. So 2 times 1 is going to be 2, and 2 times negative 2 to the 9th is going to give us negative 2 to the 10. And 1 minus 2 is going to give us negative 1. We can distribute this negative 1 sign, and we will get 2 positive 2 tenths minus 2. And if we were to plug this into a calculator, we would get 1022. And that's how you can find the sum of a finite series. Okay, so now that we've learned the gist of finding the sum of a finite geometric sum problem, let's look at what a problem will look like in summation form. So the first thing that we want to do for this problem is we're going to first look at the index. Our n is equal to 1. That's one of our requirements. The next thing that we want to look at is the r. And to do that, we're going to have to find our first term. If we were to plug in a 1 into our equation, 8 raised to 1, that's going to give us an 8. If we were to plug in a 2 for our second term, we would get 8 squared. Next, let's find our r. Our r is going to be equal to the second term divided by the first term, which is going to give us 8. We can check this 8 against the requirement r is not equal 1. That is true, meaning we can find the sum of this problem with this equation. So now we can plug in our values into the equation. So we can plug in our 8 for the first term, 1 minus r, which would be the common ratio 8 again. We can plug in 73 for the number of terms, because that is our upper limit, all divided by 1 minus the common ratio 8. From here, we can begin distributing everything. So we can distribute this 8 across this parentheses. We can do 8 times 1, that's going to give us 8. And 8 times 8 raised to the 73 is going to give us 8 raised to 74. And that's all divided by 1 minus 8, which is going to give us negative 7. And that is the sum of this series. Okay, here's our next problem. Now, the first thing you'll notice about this problem is that its index, instead of starting at 1, it starts at 0. This isn't a big deal. It just means we have to re-index. All that means is we're going to increase our starting index by 1. So we're going to make our n is equal to 1. And we're going to increase the upper limit by 1 as well. So we're going to make it 701. Now, because we've done that, however, we also need to change our a sub n equation. This negative 3 raised to n, we have to make this negative 3 raised to n minus 1. This is because we need to make our first term equal to the original equation. So now that we've done that, we can begin solving as we've done so before. So we can plug in for our a sub 1, this is our first term. If we were to plug in a 1 into this equation, negative 3 raised to 1 minus 1, that'll get us negative 3 raised to 0 in parentheses, which is actually just going to equal 1. If we were to do the second term, a sub 2, if we were to plug in negative 3 raised to 2 minus 1, that would give us negative 3. So now that we've done that, we can find our r. Our r is going to equal the second term divided by the first, which is going to give us -3. Our -3 does not equal 1, meaning we can plug this into our equation. Now we can plug in our first term, 1 minus the common ratio, which is going to be 3, and we can actually change this to a plus because -3 minus a minus sign is equal to a positive sign. Next, we're going to plug in our upper limit, or the number of terms. It's going to be 701 for our n. And then we're going to divide this by 1 minus 3, and that's just going to give us 1 plus 3. And then we can simplify this, and we'll get 1 plus 3 raised to 701 divided by 4. And this is the sum of this problem. Okay, here's our next problem. So this problem, like the last one, its n does not equal 1, and we want its starting index to start at 1. To do that, we have to take away a 1 from the starting index and the upper limit. So we take away a 1 from the starting index, we get a 1. Because we took 1 away from the starting index, we also have to take a 1 away from the upper limit, giving us a 24. We can rewrite our a sub n, but we need to add a plus 1 because we took away a 1, and we want the first term of this series to equal the first term of this series. Now we can begin solving. Our a sub 1 is going to equal 1 divided by 6 squared, and our a sub 2 is going to equal 1 divided by 6 cubed. From here, we can find our r. Our r is going to equal the second term, which is going to be 1 divided by 6 cubed times 6 squared. I'm just skipping ahead. I'm multiplying by the reciprocal of the first term because it's going to be a giant fraction. And then this is just going to give us 1 divided by 6. Okay, now that we've found everything, we can plug this into our equation. First, we're going to find our first term, which is going to be 1 divided by 6 squared. And then we're going to multiply this with 1 minus the common ratio, which is going to be 1/6. And everything is going to be raised to 24, which is the upper limit. This whole thing is going to be divided by 1 minus the common ratio. Now we can begin simplifying and distributing values. So we'll rewrite this first term times 1 minus 1 divided by 6 raised to 24, because 1 raised to 24 is just 1. And 1 minus 1/6, that's just going to give us 5/6. Next, we're going to get rid of this ugly 5/6 fraction, and we're going to distribute it by multiplying by the reciprocal. So we're going to do 1 divided by 6 squared times the reciprocal of 5/6. That's just going to give us 6/5 times 1 minus 1 divided by 6 times raised to 24. And from here, this is just going to cancel out these 6's. And then we will be left with 1 divided by 6 times 5, that's 30. So 1 divided by 30 times, in parentheses, 1 minus 1 divided by 6 raised to the power of 24. And that is the sum of this problem. Okay, so here's our final problem. This is a finite series application problem, and it says you deposit $15 each month in a bank account that pays 12% annual interest compounded monthly. How much money will you have in the account right after your 20th deposit? Now, to do this problem, we're first going to have to map out our key values. So the first thing that we want to map out and underline is our $15 each month. That's going to be our first term. This is going to be 15. And this is because we're depositing $15 each month. So for the first month, we're going to deposit $15. Thus, it's our first term. Next, we're going to look at our common ratio. Now, our common ratio is 12% annual interest. Now, to find what this would actually be for our R, we're going to have to use a little bit of math. So we're going to turn this 12% into a decimal. So we're going to turn this into 0.12. And because it's compounded monthly, we're going to divide it by 12. Now, we're not done here because the interest is increasing our money, we're going to have to add a 1 to it. And then this is just going to give us 1.01, and that's our common ratio. And the final thing that we want to underline is going to be our 20th deposit, meaning our n is just going to be equal to 20. Okay, so now that we've written everything out, let's first write out what this actually means. So for our first deposit, I'm just going to write a 1. We're just going to be depositing $15. That's it. There's no interest rate, nothing's compounded. It's just going to be $15. This is right after we deposit $15. After our second deposit, we're going to deposit another $15, but the first $15 we deposited is now going to be compounded monthly. So it's going to have some interest. For our third month, right after it, we're going to add another $15. The $15 that we added the second month is going to be compounded monthly. And our original $15 from the first month is going to be compounded twice, and it's going to be squared. And so this is going to continue all the way down until we get to the 20th deposit. And that's just kind of to help you visualize it. So now that we've done that, we can begin plugging this into our equation a 1 minus r raised to n divided by 1 minus r. So to do this, we're going to plug in our first term, which is going to be 15. Then we're going to plug in 1 minus the common ratio. Our common ratio is 1.01. And we're going to raise this to our n, our upper limit, our 20. And finally, we're going to divide everything by 1 minus the common ratio. And this is our answer. This is how much we will make right after our 20th deposit. And that's how you solve this problem. So thanks for watching. Catch you later.